So in this tutorial we're now going to deal with titrations that are between a weak acid and a strong base. You can also do something similar if we're dealing with a weak base and a strong acid. It will be similar, but again, just as you've seen in previous examples and previous tutorials, the only thing that will change is whether you're dealing with hydronium concentration or hydroxide concentration, so you do have to be careful of that. So first, just to show you what one of these titrations looks like by using a titration curve, you'll notice first off that the pH in this particular diagram, or this particular titration curve, it begins a little bit higher than what you may have seen in the other tutorial when we dealt with strong acids and strong bases. It is happening in this case at about 3 for a pH, and before it was beginning more at a 1, I believe. So that's one change you might see. You might also notice that this curve is, it looks like it shrunk a little bit, where it's closer together, whereas with a strong acid and strong base, it's a little bit more spread out, because you have such a, a larger pH range that's occurring, whereas something with, a weak acid or a weak base, you're not going to get that big of jump as you saw before. So equivalence point in this case again happens right in the middle, so make sure that you pay attention to that, and in this case we have a pH 8.78. Now as far as indicators go, it's especially important now to be able to figure out the correct indicator, because you don't want to use something that's way below the pH, or else you're not going to be able to get a good idea of the change that's happening. So for example, using the same indicator, the beginning indicator that we used in the previous example, you're able to see that the range that's happening here, or the color change that's happening, happens completely before the equivalence point even occurs. It's happening, once you're beginning to see the gradual incline of pH, but it's not what you need. But if you look at phenolphthalein in this case, you notice that the change is happening right near the equivalence point. So that's what that would be a correct indicator to use in this case, because of the fact that it's right there at the point of change. Alright, so let's try doing one of these calculations, which we're calculating pH as we did before. In this case, though, if you look at the acid and the base that's being used, you'll notice that you have an acid that's not a strong acid, and you have a strong base. So right off the bat, you can probably figure out that you're not going to be using the easy type of calculation that we did before. In this case, because of the fact that it's a weak acid that we're dealing with, we are going to need to use the ice table in some way. But that's actually going to come, a little bit later on in this calculation. We do need to first do something else, though. We need to first figure out how much of, we're starting off with this particular acid. We need to figure out what the salt is going to be, at the very end. So we do have to determine that amount. And to do that, we are going to actually deal with stoichiometry a little bit, so it's coming back to haunt you a little. So first thing though, just take your liters, so it's 0.025, and you're going to multiply that by the 0.1. That way you're able to get the moles of this particular acid. And then after that, we want to multiply by some ratio of moles between the acid and its salt. Well, in this case, it's really just a 1-to-1 ratio. We're not seeing any change in that. If you had something like H2SO4 or H3PO4, then you'd see a different ratio. But in this case, it's just going to be 1-to-1. So you have 1 mole of, and we'll just say NiC, 1 mole of that particular salt over 1 mole of its acid. So if you were to do out this math, you'd end up with 0.0025 moles of the salt. But the problem is we don't want to have just moles. We want to be able to have the the concentration of this. So we are going to have to divide this by some volume. Well, in this case, we already know that we added 25 milliliters of the acid. How much of the base did we add, though? Well, because this is at its equivalence point, though, we're able to kind of see, what the volume is going to be for the sodium hydroxide, because of the fact that, again, equivalence point is just basically the number of moles of acid equals the number of moles of base. Well, if you have 25 moles of 0.1 of the acid, then that means you'd have to have 25 milliliters of 0.1 sodium hydroxide as well, because of the fact that then the two will equal out. So knowing that, the total for the volume in this case is going to be 50. So divide that by 50 and you end up with concentration for the salt as 0.05. So now you're just going to do a regular salt ice table, as you did back in lesson 3, where first take your salt, so it's just NiC, negative. It's being ionized in water, so do that. And then on the other side it's going to form HNiC and OH minus. So you have that. Now start filling it in. And for the NiC minus, you'll put in the concentration that you just determined. So it's 0.050. Water never matters. And then you start off with 0 on the others. So minus x, 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 0.050 minus x, x, and x, like that. Now in this particular problem, they gave you the Ka, or the expression for the acid. You have OH though in this case, so that means you need to find the Kb. So you would just do the 1 times 10 to the negative 14, divide that by the Ka that they gave you, which is 1.4 times 10 to the negative 5th, and so that should give you 7.1 times 10 to the negative 10. So that's your Kb. So once you know your Kb, now you can go and actually put this into the expression and solve for x. So you have 7.1 times 10 to the negative 10 equals, it'd just be x squared over 0.050. We're getting rid of the negative x because we don't need it. And then if you were to find your x, in this case, it'd end up being 6 times 10 to the negative 6. Now if you refer back to your ice table though, you can see that that is for OH. So if you were to take the negative log of this, that would actually just give us the POH for this particular solution. So now we want to go and figure out the pH though. So it would be 14 minus 5.22, and so we get 8.78. Alright, so let's try doing another example. In this case, again, look to see what you have first, whether you have strong acid bases, whatever. So in this case, we notice that we have HF when we have NaOH. HF is weak, NaOH is strong, so you will have to do your ice table and everything else. First thing we want to do is just figure out the number of moles of the F minus, in this case, or the salt solution. So we go 0.025 times 0.1 times, now again it's going to be a 1-to-1 ratio because you just have 1 mole of F minus to every 1 mole of HF. So we do that, and we end up with 0.0025. So that is the moles for, or those are the moles for the F minus. We need to figure out, though, the volume in this case. Which to do that, it's not as easy as what it was before. The other one we were just able to, kind of set them equal to each other. This case, though, we have 0.1 molar HF and we have 0.15 molar of NaOH. So we're not able to do that. What we could do, though, is just take the 0.025, multiply it by the 0.10, and set that equal to 0.15, and then we're looking for the number of moles like that. Or not the moles, sorry, the volume. So you're looking for the volume of the base in this case. So do that out. So it would be 0.025 times 0.1 and then divide by 0.15. So you end up with a volume of 0.0167. So 0.0167 plus what we had originally, which was 0.025, and you end up with a total volume of about 0.0417, like that. Now this particular equation up here might look familiar. That was the equation that we used way, back in Unit 4 when we dealt with types of reactions. It was just the M1V1 equals M2V2. And I'm just showing you now that, again, at the equivalence point, the moles of the acid equal the moles of the base. So if you do this, you're able to figure out the amount of the volume that it takes to be able to get there. So if we were to do this, this will come out to 0.060 for the F minus, and now we can go and set up our ice table. So again, we're dealing with our salt first, so you have F minus, put that in water, and you have HF plus OH minus. So because of the fact that we have OH minus, we know that we need to change our Ka over to Kb. And actually I didn't give you a Ka, but in this case Ka for this particular reaction is 6.8 times 10 to the negative 4. So if we were to change that over, the Kb in this case would be 1.47 times 10 to the negative 11, like that. So now let's do our ice table, which I probably should have done before, but so for your F minus, you have what we just figured out, which is 0.060. You don't worry about water. You have 0, minus x, 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 0.060 minus x, x, and x. Plug that into your Kb expression. So 1.47 times 10 to the minus 11 equals x squared over 0.060. So you end up with an x of 9.39 times 10 to the negative 7. That is the amount of your OH. So if you would take the negative log of that, that'll give you the POH, which POH would be 6.03. Minus that from 14, and you end up with a pH of 9.79. So that's just the way of being able to do a weak acid, in a strong base, the type of titration calculation that you'd have.